that one yet, so I gotta find that. Yesterday we started surface integrals. We're focusing on integrating a scalar function. Today we're going to look at flux. And so evaluating a vector field across the surface. So if we want to evaluate flux of the field 18z, negative 12, 3y, across the part of the plane 2x plus 3y plus 6z equals 12 located in the first octant. It's not specifying orientation, so by default we assume outward pointing normal vectors. So we're calculating the outward flux. We can write our surface as a function of x and y. Parameterization would then just be x, y, and the function. As for the domain, we're in the first octant, so both x and y will have to be non-negative. If we set z equal to 0, solve for y, should be 2x over 3. 4 minus 2x over 3. And then x, we're going to go from 0 to 6 if both y and z are 0. 2x equals 12, x equals 6. Put that as x, y. Should I? We now need the normal vector. For outward pointing, call that function of the surface, g of x, y, negative partial g partial x, negative partial g partial y, 1. I'm going to specify outward flux here. Now double integral over our domain D of the vector field evaluated at G. G is 2 minus x over 4 minus y over 2. There's no x there. And x and y would both stay the same anyway. Dotted with n. dA. Just write this. That's what that first component would be. X went from 0 to 6. Y went from 0, what was it, 4 minus 2x over 3. 4 minus 2x over 3. Now take the dot product. 1/3 of that. 12 minus 2x minus 3y. Minus a half of 12. Plus 3y. Minus 6 is 6, minus 2x, and the y's cancel out. Integrating with respect to y is going to be nice. Make things a little bit nicer. Can factor a 2 out from the first term. And just to get rid of the fractions, let's factor a 2/3 out of the second term. Four divided by 2 is 2 times 3. 6. FOIL that. 18 minus 9x plus x squared. What is 18 times 6? 60 and 70, no, 60 and 48, 108. It's going to be in 9 halves. And then 36. 18. So 9 times 8. Oh, sorry, 9 times 18. 90 and 72, right? Third was 6 cubed. Six cubed is 2 cubed times 3 cubed divided by 3, so it's 2 cubed times 3 squared, 8 times 9, 72. $180 minus 162, 18. Outward flux is 24. Outward flux of z, x, negative 3y squared z, across the surface of the cylinder, x squared plus y squared equals 16, located in the first octant, between z equals 0 and z equals 5. Recall, I actually do a cylinder in the video. So the cylinder x squared plus y squared equals 16 would be an infinite right circular cylinder extending up the z-axis, right, extending along the z-axis. We're also told that we're bounded by the planes z equals 0 and z equals 5. look at G, right, so for our purpose, let's just say, we'll generalize this. It's going to be a cylinder extending from z equals a to z equals b of radius r. Then our parameterization G is going to have a z in it, right, to represent the height. And that's, of course, the last position. What about the x and y? Well, the x and y, aren't they dictated by the circle? And what is the parameterization of a circle?
R cosine theta.
And r sine theta.
R sine theta.
There's parameterization. Now remember, r is a constant, right? So we're only dealing with the surface of the cylinder. We're parameterizing the surface, not the entire solid. So on the surface, it's the same r. So that r is a fixed constant. That means there's only two things that are varying here, theta and z. Our parameterization is a parameterization in terms of theta and z. Now I'm going to transfer that over to here. I'm writing out what the function of it anymore. What's the radius of this cylinder? There's parameterization with its domain. To find the normal vector, we need the partial of g with respect to theta and with respect to z. First, with respect to theta, what do you get? Again, I'm just doing the general one.
You mean just cosine theta, sine theta?
Of g, all of g,
R cosine.
take its partial with respect to theta.
Oh.
Now with respect to z, what do you get? Oh, that's lovely. Normal vectors, they're cross products. And then we'll just verify if it's outward pointing or inward pointing and make adjustments as necessary. The r cosine theta times 1 minus 0 going to be 0 minus negative r sine theta. 0 minus 0. Is that outward pointing? Yes. That's the outward pointing normal vector for a cylinder.
Why is it outward pointing?
So imagine the surface of a cylinder, outward pointing would be away from the cylinder, right? No matter where you are on the surface, isn't always going to be, the direction will be away, right? So for instance, at pi over 4, positive root 2 over 2r, positive root 2 over 2r, 0, that's pointing away from the cylinder, right?
Oh, okay.
If you're at 3 pi over 4, your first term is going to be negative, but that's fine because you want to be pointing the negative x direction to point away from the cylinder, right? So even there it's pointing away from the cylinder. So no matter where you are on the cylinder, you're always going to be, your vector will always be facing away from the surface. So that's why it's outward pointing.
How would you make it inward? Could you make that inward?
Negative.
Negative?
You just multiply by minus 1.
Okay.
Right, that'll just flip the direction 180 degrees. Then everything will be pointing into the surface. Keep in mind this is not a closed surface. So this top up here and this bottom are open. They're not actually part of the surface. We're just dealing with the lateral, the cylindrical. There would be the normal vector. So now we can set up our flux. Evaluate the vector field along the parameterization. Z is Z, X becomes 4 cosine of theta, then negative 3 Y squared is 16 sine squared of theta, Z is Z. And then dotted with, I don't have enough room. Perform the dot product. 4z cosine theta plus 16 cosine theta sine theta and then plus 0. And there's a mistake here. if you find what the mistake is. It's in the parameterization. Specifically in the domain.
The Z.
They only goes 5 to 2. First octant means X and Y have to be positive, right? That's only quadrant 1. For the whole thing, the flux would be 0. Yeah, let's do it with respect to Z first. Do that and also factor out 4, I guess. Z squared over 2 from 0 to 5 be 25 halves. And then it's going to be 4 times 5. Subtract out 5 now. Cosine theta is easy enough. Cosine theta times sine of theta. Could do u sub, right? you also just do this? And then you sub on just 2 theta instead of an entire trig function. That's the path I'm going to take. What's the antiderivative cosine?
Sine.
Antiderivative of sine of 2 theta.
Is a negative cosine of 2 theta.
You're missing something. Over 2.
Oh.
And then get rid of the net push and get rid of that too. What is sine of pi over 2? Sine of 0. That first term is just 5/2 times 1. What is cosine of pi? Cosine of 0. That second term becomes -2. Minus -2. Yes. The double angle identity on sine. Sine of 2 theta is twice cosine theta sine theta. Which means cosine theta times sine theta would be half sine of 2 theta. From here, yes, I factored out a 5. So 5/2 and 2 is 9/2. Times 20 is 90. I'm going to skip that one. I'll let you do that on your own. I want to get to this one. Vector field. It's for xz, negative y squared yz. We want the outward flux of that through the surface of the unit cube. That is the best cube I've ever drawn. Save that in personal fridge or something. Just straighten it out a little bit. But I try to do too much and erase my other work, so. Yeah, good enough. For the unit cube, that point right there is the origin. And so it's coming out, going up to the right. Unit cube, what do you think the length of the sides are?
1.
Right, so it comes out 1 unit, up 1 unit, to the right 1 unit from the origin. Now we want the surface of the unit cube. Isn't a cube composed of more than one surface? How many surfaces is on the cube?
6.
6 of them.
They're all equal.
The surface areas are, but we don't care about surface area. We're doing flux. That means we have to find the flux through each of the 6 surfaces and add them together. That's 6 flux integrals we have to calculate. This is a closed surface. Right, so using similar notation, you could see something like this as well to represent that the surface you're working with is closed. All right, just like with line integrals, right, you had a path that was composed of multiple non-overlapping paths, then your line integral was the sum of the integral on each individual path. Same thing with the surface. If your surface is composed of more than one non-overlapping surfaces, then your total surface integral is the sum of each. Okay, so let's do front first, the front surface. Well, if we're dealing with the front surface, isn't our x going to be 1? Right, because it's just that square. So y is going to change and z is going to change. But what does y and z range from?
0 to 1.
0 to 1, both of them, right? Very common notation in math. That means that both y is between 0 and 1 and z is between 0 and 1. Now what about the normal vector? We want outward pointing. So what direction does the vector have to point?
To the origin. Or away from the origin.
But more specifically, how is it pointing away from the origin? We could just do the partials, right? G sub y is 0, 1, 0. G sub z is 0, 0, 1. What's their cross product? One, 0, 0. As the face in the positive x direction is going to have a length of 1 because we're dealing with a unit cube. Look at the back. What is x in the back?
0.
But then y and z would be the same, right? What is the normal vector?
Is it still z hat?
I will be pointing inwards. Now it has to be negative I, right? You want to point away from the surface, right? So you're having it point away from the back, which means it has to point in the negative x direction if it's pointing away from the back. Right? Positive x direction, you're coming into the surface. Let's look at the right side. We're on the right side. So this part here, right? Which one's fixed?
Y.
What is y?
1.
What do x and z go from?
0 to 1.
And what is our normal vector? So which direction does it have to face? The positive what direction?
Is it positive y?
Positive y. So it's pointing to the right. Again, it's going to be 1 because it's unit cube. If you now look at the left facing, what's y?
0.
what's the normal?
Is it negative? J.
You have to point in the left direction. Look at the top facing. Which is fixed now?
X, Y, or Z is fixed at 1.
And what's the value of Z?
1.
X and Y go from what?
0 to 1.
And what is the normal vector?
Wouldn't that be
What is it? Positive what?
positive Z, right?
Which is what vector?
Z, 0, 0, 1.
Which is what? Go away, go pilot.
Or, just K hat, yeah.
K hat, 0, 0, 1.
Okay, the first one was I hat.
Yes.
Okay, that's what was confusing me. I thought that was a Z. Gotcha. No,
Those
the,
are my
nor-
Z's.
the normal.
Those are my Z's.
Okay, that looked like a Z. Yeah,
I put a line through my Z
yeah,
for that very reason. So.
yeah. I don't do that. That's why.
Make the unit vectors curly so that I can distinguish between, is that a vector or an I? A variable I. All we do is one facing left. Bottom facing. And what is N?
Negative K.
The total outward flux is a closed surface integral. Again, for the power of technology, I can just copy and paste. That will be our total outward flux. Sum of those 6 flux integrals. So double integral for the outward or the front domain. We have to evaluate our vector field at the parameterization, but the parameterization is easy. X is 1, y and z stay the same. So it'll be what? 4z negative y squared and then yz. Dotted with n dA. Now the outward domain, or the back domain, sorry, the back domain, x is now 0. Sorry. Negative 1, 0, 0. Domain for the right facing. This time, y is 1. X and z stay the same. Dotted with n, dA. Y is now 0. Right? The top facing, z is 1, x and y stay the same. Now finally for the bottom. Z is 0. X and y are the same.
So half of them are just 0.
This is a really nice one. The back, left, and bottom all evaluate to 0. That doesn't mean that the vector field doesn't flow through it. It just means that the net outward flow net outward flow is 0. So it could be that you have equal inward and outward. Right? The amount going in is equal to the amount going out. Cancels out to 0. That's all that means. So remember, this is a net flux. It's always just calculating net flux, not necessarily an actual flow. I don't want to duplicate it. New slide. That's just going to be 4z, right? Then it's going to be -1. Oh, that's nice. And then just y. Well, the y is just going to go to 1, right? That would be left with 4z. That's just going to be -1. And that last one wind up just being that single integral, right? Because if you value with respect to x is just 1. That makes this a lot easier. 2z squared from 0 to 1 is 2. Y squared over 2 from 0 to 1 is a half. Outward flux is 3/2. So again, on how it was designed, it was a really nice surface integral to do. Right? It was a unit cube, and it was written in such a way that half of them went to 0. You can imagine how much of a pain it would be on. Now it's not a unit cube, let's say. It's still a cube, but not unit. And it's a more complicated vector field, and it's closed. Now, if it was an open top, then we don't have 5 to worry about, right? You won't have that top surface at all. And again, now, just what is the what's the 3-dimensional octagon?
I don't know that.
There, each of the facings is an octagon. I think it's going to wind up being 8 cubed, so 8 cubed total surfaces
Oh my god.
that you have. Find the outward flux of that. Good luck, have fun. Actually, that wouldn't necessarily be as difficult as it sounds because we're going to study a theorem that lets us do closed surface integrals a lot easier.
Would the octagon also have a bunch that just cancel out to 0?
It depends on the vector field.
If it's a
It depends on the field and the normal vectors. So maybe, maybe not. If they're be hideous, I just need to have to. Do still have some time. And I really do appreciate these just yet, but I will get them up there. I introduced the differential forms of Maxwell's equations last time. This puts them with their integral forms. To actually fully appreciate these, though, I am going to need to go through Green's theorem, Stokes' theorem, and divergence theorem. That's kind of how they're related. And for instance, this is a divergence theorem problem, as is this. These two are divergence theorems. These two, I think, are Stokes. Green's or Stokes, depending on if it's two-dimensional or three-dimensional. But there are Maxwell's equations, along with what the equations actually are, which are called. See if I can get what each of those constants stand for. Those. I just show each of those it's representing. You know, maybe I'll ask you to write out Maxwell's equations. Any questions on surface areas? Space 18, so that. So that fourth project was the last project. There wasn't anything for vector fields, unfortunately. I'd have to really go searching for it and force enough, I guess. We only have 2 weeks left. Next week we'll be after.
And then finals.
Yeah, and then finals. I don't really count that as 2 weeks of lectures. We only have to cover 3 more things: Green's theorem, Stokes' theorem, divergence theorem. That's what we spend the next 2 weeks doing.
Is the final just going to be everything after the last test?
I'll talk about it.
Yep.
So I'll talk about it as it gets closer. Probably mention it when I hand out the reference sheet, which I do plan on doing next week. I already wrote it.
Is it too hard?
I don't think it is.
Okay.
Then again, I think,
Well,
I didn't think
yeah,
the second exam was, I mean, second exam was hard, but I didn't think it was that hard. It is only 5 questions. Oh, guess I'll tell you. There's going to be extra credit on it. So the exam is comprehensive. But the mandatory part's only since the second exam, and that's 5 questions, 50 points. Then there's 2 extra parts. Each one worth 5 points for the first part. The part 2, you can get 5 points added onto the first exam grade, and part 3 lets you get 5 points added onto the second exam grade. So it is comprehensive in the sense that I'm covering everything, but only since exam 2 for the actual mandatory part.
That's cool.
So you have a chance to increase your exam 1 and 2 scores by 10%. That's why I chose 5 points, 10%. So, I think it's fair.
Yeah.
And you have 2 hours to do it, right, instead of the 75 minutes. That's why I hate these 3 days a week. You only have 75 minutes to do the exam instead of 100. Stupid. When we come back on Tuesday, we'll look at Green's Theorem. Have a good weekend, have a good holiday. Easter's this Sunday, which I completely forgot. What my awesome Easter pie. Easter instead of today.